Let me begin with a quiet question. When you look at the sun, what do you think it is doing? Burning, perhaps. Flames in space, a gigantic fireball. That image feels natural, almost unavoidable. Fire is the brightest, hottest thing we know on Earth. So we borrow that idea and stretch it across 93 million miles. But is the sun actually burning, or are we projecting something familiar onto something profoundly different? Imagine holding a piece of wood over a flame. The wood darkens, cracks, and releases smoke. Burning is a chemical story. Atoms rearrange themselves. Oxygen meets carbon. Energy slips out in the form of light and heat. Simple, local, temporary. When the fuel runs out, the fire fades. Now pause. Ask yourself, where would the sun find enough oxygen to keep such a fire alive for billions of years? The vacuum of space offers none. Already the picture begins to wobble. So if the sun is not a chemical fire, what is it? Let me guide you into a different way of thinking. Picture a vast sphere of gas, so heavy that its own gravity crushes everything toward the center. Not gently, relentlessly. Every second the sun pulls itself inward with unimaginable force, and yet it does not collapse. Something inside pushes back, something powerful enough to resist the weight of a million Earths, pressing from all sides. What could generate such resistance? Let us go deeper. At the sun's core, matter behaves in ways that feel almost alien. Temperatures climb beyond anything we encounter naturally on our planet. Pressures rise to levels that would flatten any ordinary substance, instant something unrecognizable. Under those conditions, atoms lose their familiar boundaries. Electrons drift freely. Nuclei move like crowded dancers in an invisible storm. It is not chaos. It is a new state of order, born from extremes. Now consider two tiny particles approaching each other. Each carries a positive charge. They repel like magnets pushed together the wrong way. On Earth, they would never willingly merge. Yet inside the sun, the environment is so intense that sometimes they overcome their mutual resistance. They touch, they combine. And when they do, a small piece of mass quietly transforms into energy. No flames, no smoke, just a subtle conversion woven into the fabric of nature. Pause again. Why does this process release so much energy? The answer is hidden in the structure of matter itself. Some combinations of particles are more stable than others. When the sun forges a slightly more stable nucleus from less stable ones, the difference emerges as light and heat, not as an explosion, as a continuous whisper of transformation, repeated trillions upon trillions of times every second. Each event is tiny. Together they illuminate the solar system. But do not imagine a raging furnace. The reactions at the sun's center occur slowly, almost patiently. A single particle may wait thousands of years before participating in such a union. Does that surprise you? We often picture the core as frantic and violent. In truth, it is measured and statistical, governed by probability rather than frenzy. Energy accumulates gradually, like countless droplets filling an invisible reservoir before flowing outward. Now let us follow that energy. It does not leap instantly from the core to the surface. Instead, it begins a long, wandering journey. A particle of light may scatter endlessly, bouncing from atom to atom, changing finger again and again. It can take tens of thousands of years to escape. Think about that. The sunlight warming your face today may have started its journey long before human civilization learned to write. Time stretches inside the sun in ways we rarely imagine. As the energy moves outward, conditions shift. The dense inner regions give way to layers where gas can flow more freely. Massive currents rise and fall, carrying heat like slow cosmic weather. Bright patches appear and vanish. Magnetic fields twist through the surface like invisible ropes. The sun becomes a dynamic world rather than a static ball. Still, none of this resembles burning wood. There is no oxygen feeding flames, no ash drifting into darkness. Why then does the burning image persist so strongly in our minds? Perhaps because our brains crave familiar stories. Fire is our oldest metaphor for energy. It is easy to see brightness and assume combustion, yet the sun's power comes from something deeper, the binding of matter itself. It is not a surface phenomenon. It is a fundamental rearrangement occurring at the smallest scales. Understanding this requires us to release the comfort of everyday intuition. Now, consider another subtle point. The sun balances two opposing tendencies. Gravity pulls inward. Energy produced at the core pushes outward. If either side gained dominance, the star would change dramatically. Too little outward pressure, and it would collapse. Too much, and it would expand uncontrollably. Instead, it exists in a delicate equilibrium, maintained moment by moment. This balance is not static. It is a living negotiation between immense forces. And here is a deeper curiosity. The sun was not always this way. Long ago, before it shone, it was a cloud of gas drifting through space. Gravity slowly gathered that cloud into a dense sphere. As it contracted, the core heated until the first transformations of mass into energy began. A new kind of light emerged, not from chemistry but from the architecture of matter itself. That transition marked the true birth of the star. Yet even now, the process evolves quietly beneath the surface, hinting at changes still unfolding beyond our immediate perception. As the core slowly changes its composition, new conditions emerge. The balance shifts by tiny fractions. Future layers respond, expanding or contracting in rhythms that span millions of years. Imagine watching a clock so vast that a single tick equals the rise and fall of civilizations. We stand at one quiet moment within that immense timeline, unaware of transitions already beginning to reshape the heart of the sun. And if we look closely enough, we begin to notice that stability is not permanence. The sun appears unchanging from our brief human perspective, yet deep within, particles are constantly rearranging, slowly altering the star's future. What seems eternal is actually a long transition unfolding at a pace almost beyond comprehension. Why does this matter? Because the sun is not a fixed object. It is a process. Let me shift your attention to the idea of fuel. When we hear the word, we imagine logs in a fireplace or gasoline in an engine. Something consumed quickly, leaving residue behind. But the sun's fuel is not burned away in that familiar sense. Instead, the very identities of particles are rewritten. Hydrogen nuclei merge and become something new. Mass becomes energy. The transformation is quiet, invisible, and precise. Now pause and consider scale. The sun contains more than 99% of all the mass in our solar system. Every planet, asteroid, and comet is a minor companion compared to this immense sphere. Yet the reactions powering it occur at the level of individual particles, unimaginably small events that collectively create the star's brilliance. How can the tiniest interactions generate such overwhelming power? The answer lies in numbers beyond ordinary intuition. Picture the core as a crowded city with no empty streets. Particles collide constantly, nudged by extreme temperature and pressure. Most encounters change nothing. Occasionally, two nuclei draw close enough for deeper forces to take over. When they bind, a tiny amount of mass vanishes, replaced by energy that begins a slow outward migration. No sparks fly, no flames leap, just a quiet shift in the bookkeeping of nature. As energy drifts outward, it shapes the sun's structure. Layers expand slightly under the pressure of trapped radiation. Other regions cool and sink, forming immense currents that circulate heat. Imagine oceans made of glowing gas rising and falling over timescales that dwarf human history. These movements sculpt patterns we observe as sunspots and bright flares, reminders that the star is alive with motion rather than static combustion. Let us ask another question. If the sun is not burning, why does it have a surface that appears to glow like fire? The answer is subtle. The outer layers are hot enough that atoms emit light naturally. When particles jostle and collide, they release photons, tiny messengers carrying energy into space. The glow is not the product of flames consuming fuel, but of countless microscopic interactions, radiating accumulated energy outward. Now imagine shrinking yourself to the size of a particle within the core. You would not see flickering flames. You would experience relentless pressure from every direction. You would feel the constant motion of surrounding particles, a dense and luminous sea where boundaries blur. Time would lose its usual meaning. Events would be governed by probability rather than intention. From that perspective, the sun would feel less like a fire and more like a vast evolving environment. Consider also the role of gravity, often overlooked when we think about light and heat. Gravity is the architect that makes everything else possible. Without its inward pull, particles would drift apart and reactions would cease. Yet, gravity alone cannot explain the sun's steady shine. It collaborates with the energy released from deep transformations, creating a balance that maintains the star's size and brightness over billions of years. Let us change perspective once more. Think about the sunlight reaching Earth today. It left the sun's surface only minutes ago, yet its origin lies in events that began long before recorded history. Each photon carries a story that started in the dense core, wandered through layers of chaos, and finally escaped into the quiet of space. By the time it reaches us, its violent birthplace has softened into gentle warmth. Another curiosity emerges when we consider longevity. A chemical fire the size of the sun would exhaust itself quickly, perhaps in a few thousand years, yet our star has shone steadily for more than 4 billion years and will continue for billions more. The difference arises because nuclear transformations release vastly more energy than chemical reactions. A small change in mass produces an enormous output, sustaining the star far longer than any ordinary fire could endure. Now reflect on how this understanding reshapes our language. Words like burning and flames belong to everyday experience, but they can hide deeper truths. The sun is not a campfire in the sky. It is a natural lateral where matter explores its most fundamental possibilities. Its brilliance is a consequence of forces operating at scales both immense and microscopic, bound together in a delicate evolving equilibrium. Yet even this picture is incomplete. The sun's interior is not uniform. Different regions host different processes, and subtle variations ripple outward over time. Waves of pressure travel through the star like distant echoes. Magnetic fields twist and reconnect, releasing bursts of energy that reach far into the solar system. These complexities remind us that the sun is not merely a source of light, but a dynamic system constantly reinventing its internal patterns. And here is a final thought to carry forward. Every atom in your body was once forged in a star through processes related to those unfolding in the sun. Today, the light warming your skin is part of a cosmic cycle connecting matter, energy, and time. When you look upward, you are not witnessing a fire, but a profound transformation embedded in the structure of the universe itself. And as we continue to explore what truly powers that transformation, we begin to notice how small changes in the core ripple outward into vast consequences, altering brightness, reshaping magnetic storms, and influencing the space surrounding every planet. These adjustments occur so gradually that entire species may rise and vanish without noticing a shift. Yet the evidence is present for those willing to look deeper, to question familiar metaphors, and to wonder whether our understanding of stars is only the beginning of a much larger story. That larger story continues quietly within layers we barely understand. Deep beneath surfaces, pressures rise and fall like cosmic breathing. Each fusion event shifts balance between gravity and outward pressure. Imagine standing inside currents, carrying heat like vast invisible oceans. How does stability emerge from endless motion instead of stillness? Particles collide constantly, yet rare encounters unlock deeper transformative forces. Old energy struggles outward through dense, crowded, luminous interior layers. Heat differences drive convection currents rising and sinking like lungs. Twisting magnetic fields store tension that snaps into sudden flares. From Earth, flickers appear while deeper processes unfold far below. Inside the core, particles wander, collide, separate, and reunite endlessly. Gravity presses inward, while radiation pushes outward, seeking fragile equilibrium. Tiny changes accumulate slowly, reshaping structure without dramatic visible surface alterations. What appears steady actually hides countless adjustments unfolding beyond immediate perception. Pressure waves ripple through layers like echoes traveling within enormous bells. Each wave carries information about hidden regions never directly observed. By listening carefully, scientists infer structures buried far beneath glowing surfaces. The sun becomes understandable through patterns rather than direct physical exploration. Still, uncertainties remain, inviting deeper curiosity about unseen processes guiding evolution. Every unanswered question opens pathways toward richer understanding of stellar behavior. Consider how density changes gradually from core toward distant luminous edges. Matter becomes less crowded, allowing energy to travel more freely outward. Photons scatter repeatedly, forgetting their origins through countless unpredictable interactions. By the time light escapes, its history becomes blurred beyond recognition. Does that loss of memory matter for understanding stellar interiors? Perhaps patterns survive even when individual stories vanish into statistical uncertainty. Scientists decode vibrations traveling through the star like distant resonant music. These vibrations reveal density differences otherwise hidden from external observation alone. Listening to stars becomes another method of exploring invisible cosmic interiors. Through careful observation, hidden structures emerge slowly from patterns within motion. Imagine magnetic loops rising from deeper layers like invisible twisting ropes. They store energy quietly until sudden releases create brilliant, energetic eruptions. Such events remind us that equilibrium remains dynamic rather than perfectly balanced. Beneath apparent calm, stresses accumulate gradually through subtle internal rearrangements. When tension breaks, streams of particles rush outward into surrounding space. These storms influence planetary environments, despite originating deep within stellar atmospheres. Yet even dramatic flares represent surface symptoms rather than fundamental energy sources. The deeper engine remains continuous nuclear transformation, shaping the sun's persistent luminosity. Surface violence distracts from quieter processes, sustaining long-term stellar stability. Understanding requires looking beyond spectacle toward subtle mechanisms, guiding ongoing evolution. Think about how rotation affects internal motion and magnetic field generation. Different layers spin at slightly different speeds, stretching invisible magnetic structures. This differential motion introduces complexity far beyond simple spherical symmetry assumptions. Over time, twisting fields amplify, reconnect, and reorganize into new configurations. The cycle repeats, creating patterns that influence surface activity over decades. Observers notice periodic variations without always understanding deeper underlying causes fully. Beneath cycles lies ongoing interaction between motion, magnetism, and internal energy transport. No single factor alone explains the sun's constantly shifting behavior completely. Instead, multiple processes intertwine, producing patterns both regular and unexpectedly chaotic. Each discovery reveals deeper layers of interdependence hidden beneath observable phenomena. Now, consider the boundary where interior energy finally escapes into open space. Here, gas is thin enough that photons travel freely without constant scattering. The visible surface emerges not as solid ground, but shifting luminous plasma. Patterns appear like boiling textures formed by rising and falling convection currents. Bright cells expand, while darker edges mark cooler descending streams beneath. Observers watch granules form, change, and vanish over surprisingly brief timescales. These patterns reveal underlying flows, transporting energy from deeper unseen regions outward. Yet beneath apparent turbulence exists statistical regularity governing average behavior over time. Small chaotic motions combine into predictable large-scale transport, shaping overall luminosity stability. Randomness and order coexist seamlessly within the sun's constantly evolving outer layers. Energy leaving the surface enters space as a steady stream of radiation. Each photon travels outward, carrying information about temperature and surface conditions. Some photons eventually warm planets, drive climates, and support biological ecosystems. Others wander endlessly through interstellar darkness without ever meeting another world. The sun radiates equally in all directions, indifferent to destinations of energy. This impartial emission reflects underlying physical laws rather than intentional cosmic design. Even so, local environments respond differently, depending on distance and atmospheric composition. Earth receives a balanced amount, enabling liquid water and complex chemistry. Slight variations could transform climates dramatically over geological timescales. Thus, stellar output influences planetary futures without conscious direction or awareness. Consider how scientists model stellar interiors using simulations guided by physical principles. They adjust parameters, compare predictions with observations, and refine theoretical frameworks gradually. Models reveal how temperature, density, and composition evolve over billions of years. Yet uncertainties persist because small variations produce large differences across immense timescales. Continuous measurement helps constrain possibilities, but never eliminates all remaining unknowns. Each new instrument reveals subtle features previously hidden beneath observational limitations. The process resembles detective work rather than straightforward mechanical calculation alone. Evidence accumulates slowly, guiding revisions to long-standing assumptions about stellar behavior. Scientific understanding evolves just like the stars themselves, shaped by ongoing discovery. Curiosity drives refinement, ensuring knowledge remains provisional rather than permanently fixed. Imagine future changes, as hydrogen gradually becomes less abundant within central regions. As composition shifts, pressure balances adjust subtly, altering core temperature and density. The sun will respond by expanding slightly, changing luminosity over unimaginably long periods. These changes occur gradually enough that life evolves without sudden catastrophic disruption. Still, long-term consequences reshape planetary environments beyond human timescales of experience. Stellar evolution reminds us that stability exists only within temporary cosmic contexts. Every star follows pathways determined by mass, composition, and internal physical laws. Observing different stars offers glimpses into possible futures awaiting our own sun. Comparative study transforms distant observations into mirrors reflecting potential long-term transformations. Through this perspective, stellar life cycles become narratives unfolding across cosmic history. And yet, many mysteries remain unresolved within layers inaccessible to direct measurement. What subtle processes influence long-term magnetic cycles beyond currently understood mechanisms? How do small fluctuations amplify into large-scale variations, shaping stellar weather patterns? Could unknown particle behaviors slightly modify energy transport under extreme conditions? Each question invites deeper investigation, challenging assumptions about seemingly familiar nearby stars. The sun becomes both laboratory and puzzle, revealing complexity hidden behind ordinary daylight. Observing patiently, researchers gather clues embedded within vibrations, spectra, and magnetic patterns. Interpretation requires imagination, balanced carefully with rigorous physical reasoning and evidence. As understanding grows, new uncertainties emerge, expanding horizons rather than closing inquiry. And if we continue asking questions about the sun's inner transformations, we begin noticing hints suggesting even deeper layers awaiting exploration beyond current theoretical boundaries, still forming today.